Hi everyone. So myself, Ilan Raman, and my colleagues Arish, Jay Balu and Jatin Batra, we are not able to travel today, but they heavily contributed to the presentation and the development. So today I'm going to talk about our experience in building 5G packet processing applications using DPDK. So before I start, I'd like to thank the organizer for giving us the opportunity and share our work. So the agenda, so we'll talk about a short introduction about our company and then the problem statement, what we solved using the DPDK. And also we can look at the advantages of the commodity hardware and how we selected that and the use case which we solved, which is the 5G correlation. And we'll also look at the deployment scenarios in the telco environment. And then we'll talk about the architecture, how the DPDK is used to solve this, some of the practical learnings, and we would like to share. And then finally, we'll talk about the end-to-end packet monitoring solution from Aviz. So Aviz Networks was founded in the year 2019, and we have presence in 3 countries, USA, India, and Japan. We are backed up by prominent investors like Moment Ventures, Acton, Cisco Investments, Wistron, and other key angel investors. We have 20 plus enterprise customers globally, and we have a strong partner ecosystem. You can see some of the names here. Most of them are switch and ASIC vendors. So the value that we bring to our customers, right? We enable open source like Sonic, DPDK, and various LLMs. And we also offer a networking 3.0 stack, which is basically starting from your network aware and application aware for complete visibility and GenAI solutions. Since we offer open source, we enable customers with choice, control, and cost. So coming to the problem statement, right? So what are all the challenges faced by telecom operators for mobile traffic monitoring, right? So the mobile technologies are evolving. So the customers are looking for ways to have a unified solution so that they can monitor all these different technologies, right? Today they have a solution, but they have a solution specific to 4G, specific to 5G NSA, but they want a unified solution so that they can monitor all these different technologies. And another thing is the customers are looking for ways to horizontally scale the solution, right? Because the traffic is growing, the bandwidth is growing, so they want a way so that they can scale it. And also the other thing is traditionally there are solutions which are based on FPGA and other proprietary hardwares, but there is more interest towards software driven solutions because they can accelerate their implementation. And another thing is like the commodity hardware, right? So there are a lot of advantages with commodity hardware. So the customers are looking for ways to utilize that. And finally, the TCO savings, which is very important for any operators. So we know the problem, what we want to solve. We looked at the benefits of commodity hardware. So like the modern day CPUs, right? It supports multiple cores. We can get easily 200 cores, logical cores on a single server. And with respect to the memory, the DDR4 and DDR5, it provides high performance. And with respect to the PCI, the Gen 4 and Gen 5. It gives us like a lot of advantages. We can move more traffic from the NIC to CPU and CPU to NIC. And with respect to the NIC, So then the NIC supports different speeds today, like starting from 10 gig to 100 gig. So I listed some of the benefits of the NIC. Like there are many benefits, but the one that mentioned here are specific to our use case. Like the NICs can support multiple queues. It also has the packet parsing capability for telco traffic. As we all know, like the telco traffic is different because it has its own headers. And so we need some additional capability in the NIC to do that. And finally, hardware-based load balancing. Like we want the NIC to do the load balancing to multiple cores. So we identified the hardware that we can use. So these are all the advantages. We looked at that. And then we wanted a very robust and software, library, and DPDK is our best choice because we all know that it is supported on many CPU architectures. It is fully tested and qualified on many NICs. So we decided to build our applications using that. All right, so coming to the use case, right? One of the use case that we want to address is the 5G correlation. So, like, what is correlation? Why it is important for telco operators, right? So, if you look at the diagram here, by the way, this is a very minimal picture here because the 5G, 4G technologies are very complex. We are highlighting the specific things that we want to use to build our application, right? So in a mobile network, right, there is always, we have this control traffic and user traffic. So control traffic is the one that helps the mobile to get registered to the core network, and user traffic is where all your data that you browse in your mobile gets connected to the internet. So from the operator's point of view, right, all these control and users, they are running in a different links, and they need a way to correlate control and user of a particular subscriber. So once we do that correlation, the operators can get more benefits. Like for example, a subscriber level KPIs, operators can find out, like, and also once you do the correlation, the operators can identify the network bottlenecks, right? Because we can easily tell which subscriber or what is the congestion, which tower is more congested and all that. So the correlation helps also with application performance monitoring, and most importantly, the capacity planning, right? Since we'll be able to tell the total usage of the network, so we can operators can easily plan for the future needs. So how correlation is achieved? So basically, as I said before, there is a control traffic, there is a user traffic. So we need to extract the relevant information from the control and user and identify and maintain that information in our application so that operators can do whatever actions they can take. So all this, the N11, N4, S11, all these are the interfaces in the 5G network. We'll talk more about that. So here is one deployment scenario. So the top one here is the core network where the actual traffic is running. So as you can see here, the control traffic is running between MME and S gateway. So it runs on an interface called S11, and it is all GTPC traffic. And the user is running from E node B2 serving gateway, and the interface is called S11, S1U. And it is based on GTPU headers, right? So what the operators will do, they'll install a tap, hardware tab, or there are some other virtual tabs also, and they take the copy of the traffic running in between these nodes and feed that traffic into application, the DPDK based application that we are building. So the traffic from the core network comes to the bottom one is called Aviz service node, where the DPDK based correlation applications are running, and it will do all the processing, right? Like one application is the 5G correlation that I explained. It can do many other applications. And all this core network, right, the links are like 100 gig. So we need a very high-end solution so that we can will be able to process a lot of traffic and do all the necessary correlation. So in this case, in case of 5G NSA deployment, so these are some of the metadata that can be extracted from the control traffic, like something like the E node B and serving gateway FTAD, user equipment information, IMSI, and many other informations. We just listed a few here. And from the user plane traffic, we can extract the 5 tuples, and also we can do the bandwidth, throughput, and latency calculations. So the another deployment scenario is 5G SA. Here the difference is in 5G NSA the control is over GTPC, but in 5G SA the control is on the interface called N11, and it is all HTTP2 based transaction. So that is the main difference. And then from the user plane perspective, the interface here is N3, and the packet type is GTPU, which is same as 5G NSA. So the important thing here is like we whatever the application that we build, right, we should be able to handle all these different interfaces and different packet types. So that is the main thing, so that we have a unified solution which can handle all these different use cases. So some of the metadata that can be extracted here is from the C plane. We'll be able to get information about the RAN, UPF, user equipment, IMSI, and other KPIs. From the U plane, it is same as 5G NSA. We can get all the tuple information, bandwidth, throughput, and latency. So we looked at the problem, we looked at the advantages of hardware, we looked at the deployment scenarios. Let's zoom into the ASN, like what is the architecture we have in the ASN to support all these scenarios, right? So this is a software architecture using DPDK. So the main, it actually runs in a run to completion model. So the main part is like we split the different functionality into functions, and we run the specific functionalities on a dedicated course, right? Because as I said before, we want to handle different traffic, right? 4G, 5G NSA, and 5G SA. So we need to split the functionality so that based on the deployment scenario, based on the traffic bandwidth, we can scale our solutions. So in this case, you can see that the traffic coming from NIC 0, for example, let's say it goes to Q0, and the DPDKL core, which is running on core 0, it can do 5G or 4G classification. That is the only job of that core. And then after the classification, the traffic can be sent to another course, which is running a different functionality using RTE rings. And in this case, core 1, for example, is specific to processing of 5G NSA traffic. and core 2 here is processing 5G SA traffic. So, and in core 3, it is doing some additional data processing and data export. Similarly, for the NIC 1, right, let's say we are getting the user traffic, and the user traffic can be sent to different DPDK L cores, which is doing processing of GTPU traffic. So some of the important things here is like we need to allocate the hash tables specific to each core, right? Because we don't want any locks. So by allocating the hash tables specific to each core can operate on the hash tables, and the performance is better. Right. So we talked about how the overall architecture looks to handle different traffic types, and how what functionalities we run on each DPDKL course. Now let's say we want to scale this solution, right? Let's say initially we have, this each core can process certain amount of traffic. Now the bandwidth increases, so we want to scale the solution, right? So this is the scaled architecture. What we are doing here is two things. We need to take advantage of the RSS functionality available in the NIC. So we need to provision the NIC so that the NIC can distribute the traffic to more queues, and we also launch more cores so that it can perform better. It can process more traffic. So as you can see here, the same functionality of GTPU processing is launched on multiple cores to get to process more bandwidth. And another thing is, so if you in this we have uplink and downlink traffic in the mobile, so we need to make sure that both uplink and downlink traffic coming to the application goes to the same cores, because each core maintains the session information and other related things. So that is very important thing. So that we need to configure the NIC to load balance based on the symmetric thing. So one another use case is, yes, we have seen how the correlation is achieved, how the architecture looks for the 5G correlation. So one other use case is like subscriber aware load balancing, right? So we have this the control and user correlated, and the operators can know more about the subscribers now, but there is a scenario where the operators wants to send the correlated traffic to multiple tools for further analysis. So let's say we have 100 subscribers, right? The use case is something like this. You want to send like 20 subscriber, the both control and user of that 20 subscribers to one tool, and similarly another set of subscribers to another tools, right? So to achieve that, we have to extend our existing architecture. There is a load balancer module that is introduced in each core, so that, for example, the traffic received on this L core will do the processing, and it will identify the subscriber, it will identify the tools that it wants to send, and then it will send traffic back to the TX queue, and then packet will go out of the NIC. So here we do both packet RX and packet TX. And we also configure the RSS, and we need to make sure that the symmetric part is achieved. So these are our learnings. Actually, we have more experience in building solutions using ASICs. Like for us, this is all, in the ASIC world, the ASIC provides all the functionalities, right? From the application, we need to configure the ASIC. so that the ASIC will forward the traffic. And here it is different, right? We have to do everything in the software. So the DPDK libraries played a very bigger role, and it helped us to develop this application in a very short time, thanks to all the contributors and the community for the great work. From our learnings, right, this we talked a bit, like this RSS, right, we need to make sure that it handles the different packet types, because the telco traffics, sometimes they have different headers. So we need to make sure that the RSS is properly configured specific to the customer traffic, so that you achieve the load balancing. And again, the symmetric part, this is also very important. Otherwise, the application will not see the uplink and downlink direction. So we need to make sure that the symmetric part is properly configured. Some of other things like, so some of the NICs, they do not support certain packet types. So that is something like we started with some NIC, and later we found that whatever we are looking is not there. So we had to move to another NIC, which is where the particular protocol is supported. And there are some packages, DTP packages, which we need to install so that the NIC can parse all the telco specific traffic. So in terms of the memory optimization, so DPDK provides a well set of APIs, and we have to we can tune some of the memory configuration, some of the descriptor configuration at the NIC level, and this is again specific to the traffic. This actually helped us to get a better performance. And another thing is the memory pools, right? By allocating the memory pools per socket, we are getting a better efficiency. Actually, there is one more slide, I'll talk more about that. Also, this NUMA, we need to make sure that the memory is allocated in the local NUMAs, so that we'll get a better performance. So we also use a lot of hash tables in our application, because all the subscriber information, all the correlation, all the data is maintained in a hash table. So we use RT hash for that. And like I mentioned before, we need to do this in a lockless manner, so that we'll get a better performance. So by allocating the hash tables for each core, for each functionality, this we can achieve. And another thing that we identified is CPU isolation, because all these DPDK cores, the kernel should not involve in any of these cores. So we configured the grub to exclude these cores from the Linux kernel. Okay, the next thing, software packet parsing. So generally, the NIC, the hardware can do the packet parsing in most of the cases, but for application like this, we need to do a more deeper parsing. For example, if you look at the 5G traffic, right, GTPC or any HTTP2, we need to go beyond layer 4, where the headers are different, and we need to do all that parsing in the software, because as it's multiple levels, right? So this software parsing, we need to enable per queue. So whenever the packet is received on each queue, if the particular thing is enabled, then the software parsing will happen. So we need to make sure that the number of queues that we allocate, we need to enable the software parsing. And definitely do not use any glibc APIs. I mean, DPDK provides optimized RT APIs. So we use that, and we get a better performance. One other thing is this embedding the private data. So there is a situation like we receive the packet in one place, one core, and we do the processing. and we wanted to put the information in that MBUF so that the same information can be used in other places. And this is more custom to our application, so we found that there is a way to embed private data for each MBUF. That is something it was helpful. So, so this is the typical dual socket architecture, right? From the hardware perspective, we can see that there is socket 0, socket 1. We have CPU 0, set of cores, memory, I/O controller. So the very important thing is, let's say we receive the traffic on NIC 1, right? So whatever traffic that is received on NIC 1, it should be processed by the cores present in CPU 0. And the same time, the memory, whatever the memory pool allocated, all should come from the RAM that is connected to this CPU 0, right? This gives better performance because let's say if we process the traffic from NIC 1 in core CPU 1, that means the traffic has to go from core 0, CPU 0 to CPU 1. That actually degrades the performance. So very care should be taken so that the cores, the queues, the memory, all handled properly in your application. So like I said before, so operators install taps in the core network to get the live traffic. But then there are like different vendors, they add more custom headers, right? The traffic that you get from the telco core network, it comes with different headers like VXLAN, ERSPAN, and GRE. In some cases, they also come with proprietary headers. So we needed a generic packet parsing capability in our application, and we took advantage of the DPDK packet manipulation library. So it has, we can easily remove the headers, add the headers. You can do all the manipulation using the MBUF. So that is something helped us. So this is the this is how the Aviz packet monitoring solution looks. So the traffic actually comes from the production network. You can see that it can come from any enterprise or any data center or the mobile networks. So once the traffic comes to what we call the open packet broker, it is the solution based on Broadcom and NVIDIA ASICs. So what it does, it receives the traffic from the core network and it does functions like filtering, load balancing, and few VXLAN handling. But this is all ASIC based solutions, right? So the whatever the functions that we do here solves a few use cases. But then for more advanced processing, right, this is where the ASN comes into the picture. Whatever the DPDK based applications that we discussed so far runs here. And again, this is all the commodity hardware based solution, and it can do all the correlation, metadata extraction, and subscriber aware load balancing. So if you look at this whole model, right, we can easily scale this solution. Let's say if your core network, you are upgrading to a to handle more traffic, all we need to do is add more packet brokers so that it can do first level of packet monitoring, and then we can add more commodity hardwares and scale the solution. So this is our product portfolio, like the ASN, the DPDK based application, it actually works with packet broker. And we have other products like Network Copilot. This is our open source LLM based AI product, which is used to solve many use cases. And once is our orchestration observability platform, which is designed for Sonic and other existing networks. It can manage many different networking NOSes. And finally, FTAS is our automated testing solution, which is used to test many Sonic from different vendors. I think that's all I have. Thank you.
Thank you for the presentation. I have one question regarding that subscriber-aware load balancer. And in your presentation, you mentioned there is a load balancer running on each core. So how that load balancer is going to address, the subscriber awareness here? Why you need to have load balancer on each core?
So each core will be having information about the user and control, right? So let's say we have like 100 subscribers, right? The 25 subscribers will go to one core, and we run this load balancer so that we can identify the tools that this 25 subscribers can go. So it's like it's two parts, right? First thing is the correlation, right? I have one subscriber, there is a control plane traffic, there is user plane traffic. Now I need to make sure that both this traffic will go to one tool. So that for that intelligence, we need the load balancer module in each core.
Will it be in case if a packet end up on a wrong core, or a different core, will it be kind of hand off to the other core, which is supposed to do? Or
so that's what, right? We need to make sure that the symmetric is all done in the hardware, so that the traffic of a particular, let's say the user traffic of a particular subscriber comes to the same core. So yeah, that's how it works.
Okay.
Thank you for sharing this lessons learned. I had 3-4 small queries that I noted down. Since you mentioned you are using DDP, I am assuming you're talking about Intel NIC card.
Yes.
In Intel NIC card, there is X710, that is 40 gig, and E810. Which NIC card you were using for this activity?
So we started with the 710 and then we moved to 810.
Okay, so now you are using E810. Now, if you were using E810 and if you were using the comms package or the telco package, the RSS is based on the inner IP tuple. That is, after your GTPU or VXLAN, whatever IP, 3 tuple or 5 tuple, you will be doing RSS to get the spread. While working with one of the customers, what we noticed is, if this is my mobile, and from this I generate traffic for Meta, Facebook, Google and all, the RSS tuple is, since 5 tuple is used, it always falls on 2 different L cores. So which RSS you used, 5 tuple or UE IP based RSS? What did you use for that load balancing? Or if you use 5 tuple, since it is falling on 2 different L core, just like what my colleague asked, how did you manage to put the packet back to the same or desired core? How did you do that?
So I think that there is an option, right? In the RTE flow, we can specify the symmetry. Right?
But if you use the 5 tuple, that symmetry is broken. Then it is not RSS. That is flow pinning to the queues.
No, we don't pin the flows, right? Like we do the RSS, we configure the NIC to do the RSS based on the 5 tuple, right? If you look at the moment we specify symmetric, the 5 tuple in uplink and downlink will land on the same core.
That is a problem, because when we are talking uplink, N3, that is GTPU, but N6, which comes from the internet service provider, is NATed traffic. So you need a reverse NATL, which I assume your packet broker or TAP protocol will be giving you. That is okay, but this is Vipin's mobile. From Vipin's mobile, I'll be accessing Teams, I'll be accessing web browser, I'll be accessing Google. All will be having different source destination port numbers and all.
Yes.
So that is different flow ID. It's not the same flow ID. That is what we had seen in 2 customer. So I am just interested to understand how did you solve it with hardware RSS.
Okay, I think whatever the scenarios that we handle, it's coming to same course, but yeah, I think we can discuss more.
Sure, we'll take it separately. And my follow-up question was on the mentioning of per socket, per CPU hash table. Can you give little bit more detail? What do you mean by per socket, per L-core hash table? Thank you.
Yeah, so like as I said before, right, the functionalities are specific to each core, right? So when we let's say we want to process the 5G NSA traffic, right? We have a hash table specific to that. So that is what we mean by per core, right? That whatever the processing we do for the 5G NSA traffic, all the sessions of that traffic, it actually uses the hash table of that core. So that means the write will be done only by one core.
But you already got flow pinning with DPC RSS. So it is per core, or that flow will come there.
Yes.
So that is why.
Yeah. Okay, got it. Yeah, now I got it. So the control, the control information, right? That is something the other cores can get the access.
So data plane is separate, control plane is separate.
Exactly.
Okay, thank you.
Additional questions for Ilan? If not, then I think we can break for lunch. Thank you very much.
Thank you.